check convergence of sequence an is equal to 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial plus 1 divided by n factorial. So the given if you write the few terms of the given sequence an, then the first term of the sequence is 1 divided by 1 factorial, the second term is 1 divided by 1 factorial plus 1 divided by 2 factorial, the next term is 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial, and so on. So this is the first term of the sequence a1, this is the second term of the sequence a2, and this is what the third term of the sequence a3. So a1 is equal to 1 divided by 1 factorial is equal to 1, a2 is equal to 1 divided by 1 factorial plus 1 divided by 2 factorial, so it is 1 plus 1 by 2, it is equal to 1.5, and a3 is equal to 1 plus 1 by 2 factorial is 1 by 2, and a3 is 1 by 3 factorial, it is 1 by 6, so 1 plus 0.5 plus 1 by 6, so it is 0.166. So if you add here we get 1.666. so you can observe the a1 is 1, a2 is 1.5, and a3 is 1.666, and the therefore now since a1 less than a2 less than a3 and so on, so the given sequence an is increasing sequence, monotonically increasing sequence, monotonically increasing sequence. Now in general you can also prove that here the an is equal to, if you write the an plus 1 is equal to 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial, so on. an plus 1 is 1 divided by n factorial plus 1 divided by n plus 1 factorial, and an is equal to 1 divided by 1 factorial plus 1 divided by 2 factorial, 1 divided by 3 factorial, 1 divided by n factorial, and therefore if we subtract an plus 1 minus an, then it is equal to, this will get cancelled here, and finally left is 1 divided by n plus 1 factorial. Now since n is a natural number, so this term is positive term, okay, and therefore it is greater than or equal to 0, and therefore an plus 1 minus an greater than or equal to 0, and from this we can write an plus 1 greater than or equal to an, and therefore an is monotonically increasing sequence. Now to show that the given sequence is convergent, we are going to check whether it is bounded above. We know that if the sequence an is monotonically increasing and bounded above, then it is convergent sequence, then an is convergent sequence. So here an is monotonically increasing. Now we want to show that the an is bounded above. So again we know that 1 by 3 or 3 is greater than 2. From this we can write 1 by 3 is less than 1 by 2, and therefore 1 by 3 factorial is equal to 1 by 2 into 3, okay, 2 into 3, and which is less than 1 divided by 2 into 2, which is equal to 1 divided by 2 raised to 2, because 1 by 3 is less than 1 by 2. So if you write the value of 1 by 3 is equal to 1 by 2, we get 1 by 3 factorial 1 by 3 factorial is less than 1 divided by 2 raised to 2. Similarly, we know that as 4 is also greater than 2, so 1 by 4 is less than 1 by 2. Therefore 1 by 4 factorial is equal to 1 divided by, that is of 2 into 3 into 4. As we know that 1 by 3 is less than 1 by 2 and 1 by 4 is also less than 1 by 2, so it is what, 1 by 2 raised to 3. So in general, from this we can write 1 by 4 factorial is less than 1 by 2 raised to 3. Similarly, 1 by 5 factorial is less than 1 by 2 raised to 4, and in general 1 by n factorial is less than 1 by 2 raised to n minus 1, and therefore an, which is equal to 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus dot 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 1 by n 1 by n factorial, it is less than or equal to, so it is less than or equal to 1 by 1 factorial as it is 1, plus 1 by 2 factorial is less than 1 by 2 raised to 1, plus 1 by 3 factorial is less than 1 by 2 raised to 3, 1 by 4 factorial is less than plus 1 by 2 raised to 3, and so on. 1 by n factorial is less than 1 by 2 raised to n minus 1, and therefore an is less than 1 plus 1 by 2 plus 1 by 2 raised to 2 plus 1 by 2 raised to 3 plus dot 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 1 by 2 raised to n minus 1. Now we know that from geometric series, the sum of the geometric series 1 plus r square plus r raised to n minus 1 is equal to the first term, that is a1 divided by 1 minus r if r is less than 1. Okay, so here if r is lies between minus 1 and minus 1, less than r less than 1. So here if you compare this with 1 plus 1 by 2 plus 1 by 2 raised to 2, so here r is equal to 1 by 2 and the first term is equal to what, 1. The first term of the series is what, 1, and therefore or it is the sum of the given series is equal to 1 divided by 1 minus r. So from this we can write an is less than or equal to 1 divided by 1 minus 1 by 2. Since what is here, r is equal to 1 by 2. This is a geometric series having the first term is equal to 1 and the common ratio r is equal to 1 by 2. So its sum is what, 1 divided by 1 minus r. So it is equal to, this implies, okay, an is less than or equal to 2 divided by 2 minus 1, that is an is less than or equal to 2. From this we can say that the given sequence an is, therefore an is bounded above, since it has an upper bound, bounded above, and therefore now since an is monotonically increasing sequence and bounded above, and therefore an is convergent sequence. An is convergent sequence.